Okay, now we are going to do a Miller compensation with the pole zero splitting. And so let's move to the next one. So we will call this one pole zero splitting. So sometimes we also call it Miller compensation. Okay, so as we explained during the lecture, the idea of the Miller compensation will be to add capacitance and resistance in parallel to the gate and drain of the second stage, and then the Miller capacitance basically will load the first pole, moving it to the low frequencies, and the pole splitting will move the output pole to the higher frequency. And the addition of a resistor will basically allow me to put a zero somewhere, and I will want to put it over the second pole, so that I can cancel it, and then I will have a larger difference between the output poles, the resulting poles. So let's go back to our notes here, and then what we're going to do first is we're going to add some capacitance. Okay, so we're going to add this C split, and then I could start trying with some small capacitance first, because I don't want to use a lot of capacitance for this. The capacitance is very expensive in integrated circuits because the capacitors occupy a lot of area. So I'm going to add around 100 femtofarads, that is small capacitance. Okay, and when I calculate the position of the pole, pole 1 will move to that will be -1 divided by 2 pi, that will be RDS1 times, and saying we have CDS1, CGS2, CGD1, and CGD2, and this one, it is not alone anymore. It comes with C split times 1 plus GM, and we saw that the gain was around RDS. There will be R1 plus R2. Okay, and that gives me that is a low frequency. So for the low frequency, I use this gain that seems to be quite accurate. That will move it to minus 11.4 kilohertz, so around 1 decade. Okay, move it down. For the second pole, that was a few megahertz, we saw that the position of the second pole, it is changed to minus. Now for the second pole, let's start with this. It is going to move a much more higher frequency, and then I have that the pole splitting start to take effect. In particular, if I add this capacitance, that at higher frequencies I will have the pole splitting. That is the whole idea of the compensation, and then I will have first to calculate my effective output resistance. So my effective output resistance equivalent resistance will be at high frequencies. I will have, that is RDS2 in parallel to R1 plus R2, something that we knew from before, and now it will pop up at high frequencies the 1 over GM. 1 over GM will be multiplied by a factor that depends on the capacitors. That will be CGD plus C split, that it is very large, now is 100 femtos, and then plus CGS, that is CGS2 plus CDS1, and then that will be divided by CGD2 plus C split. So we will have this equivalent resistance, and the equivalent capacitance. Also we do the calculation for the equivalent capacitance. That will be equal to CDS2 plus CL plus, and then I have this capacitor divider. So the capacitor divider, that will be CGS2 plus CDS1 multiplied by CGD2 plus C split, and that will be divided by CGS2 plus CDS1 plus CGD2 plus C split. And then the position of the new position of the pole, that will be equal to -1 divided by 2 pi R equivalent C equivalent. It will move to -22 megahertz, 3 megahertz, and okay, that is without the zero. Now so that will happen when I split I just use the capacitor. Now let's add the resistor. And for the resistor I have that zero will be located at 1 divided by 2 pi C split times 1 over GM minus R split. So I can play with the value of R split, and I can make it negative or positive this zero, and my first option will be to put it over P2 here. Okay, so if I place it over P2, then zeta is going to be equal to -22.3 megahertz. I solve for the value of split. R split is equal to 1 divided by GM, that will be GM2 minus 1 divided by 2 pi C split, and then will be the position of the second pole. And when I do the calculation, that give me 76 kilo ohms. Yeah. Okay, so let's write down these values. 76 kilo ohm and a capacitance of 100 femto, and let's go to the simulator. So let's see. So let's put the values that I got from the calculation. 76 kilo and 100 femto. We connect it. And let's run it. Okay, so let's take a look for the closed loop gain, and then we see it's stabilized. Okay, very similar to the previous case. We have a stabilization, but let's take a look. We have pole at minus 14 megahertz. We have 1630 megahertz here, minus 1630 megahertz here. So we have stabilized it, but now, of course, we cannot guarantee that this is going to end up in backward positions anymore. But the system it is stable. Now we can change this behavior if we want. We can modify a little bit the value of this zero that we introduce. Let's take a look to A beta. We have in A beta we have let's put this one in log scale, and then let's take the stability now. So we go to 1, and then we see that that we have around 80 degrees phase margin, or 70 degrees, around 70 degrees phase margin. It is pretty much stable, but now we have to understand the price that we have paid for this. We have lost, I mean, we have moved the pole to lower frequency, and then we have lost loop gain at higher frequencies. So that is what we have paid as a price. So we have lost gain at higher frequencies due to this Miller capacitance, that it is basically low pass filter in the gain at high frequencies. Okay, we can of course tweak this a little bit if we don't like the transfer function. We can tweak it a little bit. We see the trajectory of the pulse here. Let's change it. For instance, we can put it something a little bit smaller, 40 kilos. So we are going to move that zero a little bit. Remember that there are actually 3 poles around, so that are interacting a lot, so we don't have only 2 poles. That we have done the assumption during our analysis, so the results will not be exactly the same as we expected. So now let's take a look here. Now they look a little bit better. The closed loop gain. So I reduce a little bit this resistor from around 70 to 40 kilos, and then look. Now I have these poles at minus 16, 17. I have one 60 megahertz, minus 60. So the poles are around backward positions, and very interesting. The bandwidth, it is not that bad. It is also approaching the ideal, minus 16, so that will be roughly 20 something megahertz. So we take a look here, then we see that with this 10, the 3 dB bandwidth will be around here, around 25 megahertz, the 3 dB bandwidth. So yeah, very interesting. So we managed to put it also backward position, not backward position, but very close to backward positions, and we have a very decent bandwidth. Okay, so we disconnected again here, and let's save it.